All right, we are on chapter 14. We've been looking at equilibrium, and this is the last video of this chapter. And I alluded a little bit earlier to what happens when you have an equilibrium expression for a reaction and not everything is in the same phase. So that's what we're going to be looking at today. All right, so far, all of the examples, if you notice, were homogeneous. That means they all occurred in the same phase. A lot of times they were all liquids or aqueous, and that's what we've looked at so far. When we found the equilibrium expression, we took the products divided by reactants, and we were able to look at what that size of it, what it told us. All right, so now just a little bit to make sure we have figured out what happens if you have a heterogeneous. Heterogeneous means it's going to be at 2 or more phases. All right, and so example here, you can see the rusting of an iron nail occurring. Okay, the iron's a solid. You have the gas of the oxygen. Water's a liquid. All right, so we're at different phases here. What happens for that? All right, so if we have this reaction right here, we have carbon dioxide. It's reacting with solid carbon and forming carbon monoxide. Just doing what we've been doing previously, we could say, all right, let's write the equilibrium expression, and we would write products over reactants. So let's just go through that, and I would say, okay, well, this is CO, okay, divided by, squared, got our balance equation, divided by CO2 and C. All right, that's what we would have done, and now we're going to say, nope. Not right. Okay, so what's different? I'm going to show you what we were going to do correctly, and we will do it like this. We will say, oh, it really is just the CO concentration squared divided by the concentration of CO2. What's different between these two? What did I leave out? All right, you should be able to see that we left out the concentration of C. Now, why is that? Well, if you notice, we have two things in the gas phase, and that carbon was in the solid phase. All right, so why did we leave this out? The K equilibrium excludes pure liquids and pure solids. On the right-hand side of the equilibrium expression. So on the right-hand side. All right, so what in the world does it mean and why? All right, sorry, I'm going to pick up my little examples. I have a block of aluminum right here, okay, and it's not too big, but a small little block. I also have just a really tiny little piece of aluminum as well. All right, they're both aluminum. What is the density of this? We can find its mass, okay, and we can find its volume, and we can calculate its density. The density of pure aluminum is 2.7 grams per milliliter. I can also, okay, find the mass of this tiny little piece, probably using water displacement because it's kind of irregular structure. I can find its volume as well, and I can find its density. Just because it's bigger and this one's smaller, will they have the same density, or will the density be different? You all should know this already. The density of aluminum is a constant, right? It's mass divided by volume. Okay, this one will have a bigger mass and a bigger volume. This one has a smaller mass, smaller volume. But when we take them both mass by volume, we will get 2.7 grams per milliliter in both cases. What we just found there is that the concentration, okay, and when we're talking about solids, usually that's talking about its density, doesn't change. Just because you use some of it up, it didn't change its density, okay? Same thing with a liquid. If you have a liquid, just because you use some of it up, its density has not changed. Now, when you talk about gases and you talk about things that are in aqueous solutions, all right, the volume really, you fill the container if it's a gas, or the volume doesn't change, but you might have used some of the moles of it up. So its molarity does change. Okay, so when you are writing the equilibrium expression for things that are solids and liquids, they stay constant. And we want to move all the constants to the left-hand side of the equation, and on the right-hand side, you only put the concentrations of the things that change. All right, so let's go and just look at that and see how this plays out here, you can see that this would be what we would normally have written. We can say that, hey, this is a constant because the concentration of the carbon, it was a solid, it doesn't change. So we can move this to this side of the reaction, and that's what you have here in the next slide. Okay, multiply both sides by C, and C cancels out. And so then you have all the constants here on the left, and any of the concentrations that will change on the right. And this is what you want to do, and then this will call, okay, this becomes just K equilibrium. So it's not like the concentration of carbon is left off, it's just it gets incorporated into the K equilibrium. All right, that should be good. I think that makes sense for everybody. Concentration, solids and liquids do not fill their container, so their concentration or their density doesn't change. Keep that with the constants. So when you are writing these equilibrium expressions, make sure you pay attention to the phases. If you have something that's a solid or a liquid, you do not want to write it in your expression. You only put the products divided by reactants for the things that change, so they should be all in the gas or the aqueous phase. All right, I think that brings us to the end of this chapter. So here's all the stuff that we have been able to get through in this chapter. We've been looking at equilibrium, what it means, the equilibrium constant, its value, what that tells us about the reaction. We also looked at what happens when you stress out a reaction and how it adjusts to that. And then the last thing we just looked at is heterogeneous reactions and what that means for writing the K equilibrium constant. So there you go. That's it for chapter 14.